The night is still a vast emptiness, stretching beyond the edges of imagination. You're floating in a void so absolute, there is no up, no down, no light to guide you, just an endless, silent nothing. Then, in a heartbeat, a spark ignites a blinding flare of energy that erupts into existence, flooding the darkness with heat, matter, and the seeds of everything that will ever be. Stars will burn, galaxies will spin, and you somehow will one day stand on a small blue planet, wondering how it all began. This is the Big Bang, the cosmic dawn that birthed the universe 13.8 billion years ago, a moment so profound, it's not just a scientific theory, but a riddle that tugs at the heart of existence itself. Why did it happen? What came before? Tonight, as you settle into the quiet embrace of this video, we'll drift through 12 complex physics concepts, each a star in the vast sky of human understanding, crafted to spark wonder and lull you into a restful contemplative sleep. So close your eyes, let your breath slow, and let's begin our journey with the mystery of the universe's birth, a question that feels like a whisper from the cosmos, asking why there's anything at all. This isn't just a story of how the universe started. It's a puzzle that challenges everything we think we know about beginnings, causality, and never reality. Picture that moment, 13.8 billion years ago, when all that exists was compressed into a point, smaller than an atom, infinitely hot, infinitely dense. No space, no time, no stars, just a singularity. A concept so strange, it feels like the universe holding its breath. Then, in an instant, it expanded, a cosmic explosion that wasn't really an explosion, but a stretching, a blooming of space itself. As it cooled, particles formed, then atoms, then the first wisps of gas that would coalesce into stars and galaxies. This is the Big Bang Theory, the cornerstone of modern cosmology, a model built on decades of observation and mathematics. But here's the catch. It tells us how the universe began, not why. It's like opening a book to the first chapter and finding the pages before it torn out, leaving you to wonder what set the story in motion. Let's drift closer to that spark, the air around you shimmering with the heat of creation. The Big Bang is supported by a mountain of evidence, each piece a testament to human curiosity. Look up at the night sky, and you're seeing the universe's expansion in action. Galaxies are moving apart, their light stretched into redder wavelengths, a phenomenon called redshift, discovered by Edwin Hubble in the 1920s. Peer deeper, and you'll find the cosmic microwave background, a faint glow of radiation that's the aftershock of the Big Bang, mapped by satellites like COBE and Planck. These are like fingerprints, traces of a moment when the universe was a sea of plasma, cooling into the cosmos we know. Yet for all its rigor, the theory leaves gaps that haunt physicists and philosophers alike. What triggered the Big Bang? Was there a before? If time itself began with the event, what does before even mean? These questions are like standing at the edge of a cliff, staring into a void that stares back, daring you to leap. Take a moment. Let your breath carry you deeper into the void. The Big Bang's mystery lies in its defiance of our intuitive sense of cause and effect. In our everyday lives, everything has a reason. A seed grows because it was planted. A fire burns because it was lit. But the universe, it's different. Some physicists, like Stephen Hawking, have suggested it might be self-contained, its laws requiring it to exist without a cause. It's a dizzying idea, like a painting that paints itself, needing no artist. Others propose a multiverse, where our Big Bang is just one bubble in an infinite foam of universes, each with its own rules. Theorists imagine extra dimensions, curled up so tightly we can't see them, where the Big Bang might be a collision or a ripple from another realm. These ideas are speculative, beautiful, yet they leave the why unanswered. A question that feels like a melody you can't quite hum, but can't forget. Let's float in that void, the spark of the Big Bang, now a distant glow. The theory's origins trace back to the early 20th century when Georges Lemaire, a Belgian priest and physicist, proposed the idea of a primeval atom, a single point from which the universe expanded. At the time, many favored a static, eternal cosmos, but Lemaire's vision, bolstered by Hubble's observations, shifted the paradigm. By the 1960s, the discovery of the cosmic microwave background by Arno Penzias and Robert Wilson sealed the Big Bang's place as the leading model. Yet even with this triumph, the theory raises questions it can't answer. The singularity at the universe's start is a mathematical breakdown, a place where our equations falter, like a map that ends at the edge of the world. Inflation, a rapid expansion in the universe's first moments, explains its uniformity, but introduces new mysteries. What powered it, and why did it stop? Imagine yourself as a speck in that newborn universe, surrounded by a plasma of unimaginable heat. The Big Bang isn't just a scientific model, it's a story, one that connects you to the stars, to the atoms in your body, forged in ancient stellar furnaces. Every breath you take carries carbon and oxygen, born in the hearts of long-dead suns. A reminder that you're a piece of the cosmos, a fragment of that first spark. Yet the mystery of its cause lingers, a question that's both scientific and deeply human. Some turn to philosophy or spirituality for answers, imagining a divine will or a cosmic purpose. Others, like physicist Alan Guth, see the Big Bang as a natural outcome of quantum fluctuations, tiny ripples in a pre-universe vacuum that ballooned into reality. Both views, sacred and secular, grapple with the same awe. Why is there something rather than nothing? Let's explore what this mystery means, how it reshapes our place in the cosmos. The Big Bang suggests the universe had a beginning, a moment when time and space were born. If so, it challenges our sense of eternity, our need for a story that stretches forever backward. It's unsettling to think reality might have a starting line, a point where before dissolves into meaninglessness. Yet, there's a strange comfort in it too, a sense that the universe is finite, knowable, a canvas we can study, even if its edges remain out of reach. The theory also raises existential questions. If the universe began, will it end? Will it expand forever, cooling into a dark, empty void, or collapse in a big crunch, only to spark again? These possibilities are like chapters in a book we're still writing, each one a chance to wonder about our role in the story. Take a deep breath. Feel the void's silence wrap around you like a soft blanket. The Big Bang's implications stretch beyond science, touching the human heart. It reminds us that we're part of something vast, something that began in a moment of unimaginable power. Whether it was a random quantum hiccup or a deliberate act, the fact that we're here pondering it is a kind of miracle. It's like finding a single perfect shell on an endless beach, a fleeting gift that makes you pause. The mystery of the Big Bang doesn't demand answers. It invites you to sit with the question, to let its enormity wash over you like a tide. What if the universe is a one-time event, a singular symphony with no encore? Or what if it's part of a larger rhythm, one we'll unravel, never fully hear? These thoughts, heavy yet gentle, are the perfect lullaby for a curious mind, easing you towards sleep. Let's linger in that spark, the universe's first light, now a distant memory. The Big Bang is more than a theory. It's a bridge between the tangible and the infinite, a story that connects the atoms in your hand to the farthest galaxies. It's a reminder that science at its best isn't just about facts, but about wonder, about chasing questions that might never be answered. As you lie there, your body sinking into the mattress, let the mystery of the universe's birth be a guide, a soft light leading you into the night. There's no need to solve the riddle tonight or ever. It's enough to feel its weight, to let its quiet awe cradle your thoughts as you drift toward dreams. This cosmic origin is just the first star in the constellation of physics concepts we'll explore tonight. Each will illuminate another facet of the universe, revealing the strange, beautiful truths that shape our reality. From the Big Bang's fiery dawn, we'll drift to a realm where reality itself blurs, where a cat defies life and death in a box that holds the secrets of the quantum world. Picture a sealed chamber, a flicker of uncertainty within, and a question that echoes through the ages. Is the cat alive, dead, or both? Close your eyes. Let the void's warmth fade into the cool mystery of a laboratory. And let's drift into the next enigma, where the universe begins to bend. The laboratory is quiet, its air cool and sterile, lit by the faint hum of fluorescent lights that cast a clinical glow across a steel table. On that table sits a box, sealed tight, its surface smooth and unyielding, like a secret carved in metal. Inside, a cat waits. Or does it? According to a peculiar thought experiment, this feline is caught in a state that defies everything we know about life and death, existing as both alive and dead until someone dares to open the box and look. This is Schrödinger's cat, a paradox dreamt up by Austrian physicist Erwin Schrödinger in 1935. Not to torment animals, but to expose the bizarre, almost dreamlike rules of quantum mechanics. It's a riddle that doesn't just challenge our understanding of physics, it questions the very nature of reality, asking, what exists when no one's watching? As you settle into the soothing rhythm of this video, let's step into this hushed laboratory, letting the paradox's eerie mystery unfold like a whisper in the dark, guiding your mind toward a restful, contemplative sleep. This isn't a mere intellectual curiosity. It's a cornerstone of quantum physics, a puzzle that's haunted scientists and philosophers for nearly a century, bridging the gap between the tangible world we touch and the strange subatomic realm that underpins it. Imagine that cat curled up or still, its fate tied to a quantum event so delicate it seems to mock our need for certainty. Schrödinger didn't propose this to harm felines. No cats were ever at risk, but to shine a spotlight on the absurdity of quantum mechanics when stretched to the scale of everyday life. In the quantum world, particles like electrons or photons don't behave like marbles or waves. They're something else entirely, existing in multiple states at once until measured. Schrödinger's cat takes this strangeness and wraps it around something familiar, a living creature, forcing us to confront a question that lingers like a shadow. Does reality need an observer to be real? As you lie there, your breath slow and steady, let's open the box, not with our hands, but with our minds, diving into a paradox that bends the universe itself. Let's set the scene, the laboratory silence broken only by the faint tick of a clock. Inside the sealed box, Schrödinger imagined a setup as intricate as it is unsettling. A cat, a vial of poison, a Geiger counter, and a single radioactive atom. The atom is the linchpin, a speck of matter governed by the peculiar laws of quantum mechanics. In the span of an hour, it has a 50% chance of decaying, releasing radiation. If it decays, the Geiger counter clicks, shattering the vial and releasing the poison, killing the cat. If it doesn't decay, the vial stays intact and the cat lives, perhaps purring softly in the dark. It sounds straightforward, doesn't it? A simple binary, life or death, decay or stability. But here's where the world turns upside down. In quantum mechanics, until the atom is observed, it's not in one state or the other. It's in a superposition, both decayed and not decayed at the same time. And because the cat's fate hinges on the atom, the cat, too, is in a superposition, both alive and dead, a ghostly blend of possibilities, until someone opens the box and looks. Picture the box, its surface, catching the laboratory's faint light, a silent challenge to your sense of reality. This is the heart of Schrödinger's cat, a paradox that defies our everyday intuition. In the world we know, things are definite. A cat is either breathing or still. A door is open or closed. But quantum mechanics laughs at such certainties, revealing a universe where reality is fluid, a dance of probabilities that only solidifies when observed. This idea, known as the Copenhagen interpretation, suggests that observation collapses the superposition, forcing the universe to pick one outcome. Until you open the box, the cat exists in a limbo of both states, a Schrödinger's paradox that feels like a cosmic coin toss where heads and tails coexist until you check. It's as if the universe is playing a game of hide and seek, revealing itself only when you turn on the light. Take a moment to let that image settle. The box glowing faintly in your mind, its contents a mystery that twists logic into knots. Schrödinger didn't create this thought experiment to explain quantum mechanics. He meant it as a critique, a way to highlight how bizarre its implications were when applied to something as familiar as a cat. In 1935, quantum theory was still young, its ideas radical and divisive. Scientists like Niels Bohr, a champion of the Copenhagen interpretation, argued that particles only take definite states when measured, a view that seemed to make reality dependent on observation. But Schrödinger, along with Albert Einstein, found this troubling, even absurd. How could a cat be both alive and dead? What counts as an observer? A human? A machine? The cat itself? Einstein famously scoffed that he didn't believe the moon only exists when we look at it. Yet, Quantum mechanics seem to suggest just that. Schrödinger's cat was a gauntlet, a challenge to Bohr's ideas, asking, if your theory leads to such nonsense, maybe it's time to rethink it. Let's linger in the laboratory. The air cool and still. The box a quiet enigma on the table. The paradox's power lies in its ability to make us feel the strangeness of quantum reality, to pull us out of our comfortable assumptions. In the quantum world, particles like electrons can be in multiple places at once, their properties undefined until measured. Experiments like the double-slit experiment have shown this to be true. Electrons fired at a barrier act as waves, creating interference patterns, but when observed, they behave like particles, choosing one path. It's as if reality shifts depending on whether we're watching, a cosmic stage that changes its script based on the audience. Schrödinger's cat scales this up, asking, if a particle can be in two states, why not a cat? Why not a star, a planet, or you? The idea is both thrilling and unsettling, a reminder that the universe might be far weirder than we ever imagined. Let's explore the implications, letting the paradox ripples spread like waves in a quiet pond. If observation shapes reality, what does that mean for the world when no one's looking? Is the universe a collection of definite things, or a haze of possibilities waiting to be pinned down? The Copenhagen interpretation suggests that reality is incomplete without a witness, that measurement, whether by a human or a machine, plays a role in making things real. It's a mind-bending idea, one that sparked debates for decades. Some philosophers, like David Chalmers, wonder if consciousness is fundamental, a kind of cosmic glue that holds reality together. Others, like physicist Roger Penrose, argue that quantum mechanics needs a new framework, one that doesn't rely on observation to resolve its mysteries. The paradox raises questions about the nature of existence itself. Does reality need an audience, or does it hum along without us? Picture yourself standing before the box, your hand hovering over the latch, the laboratory's silence pressing in. Would you open it? What would you expect to find? The paradox also challenges the boundary between the quantum and the everyday. At the level of atoms, superpositions are real measurable phenomena confirmed by experiments like those with entangled particles. But in our world of cats, cars, and coffee cups, things seem solid, fixed. Why don't we see superpositions in daily life? This is the measurement problem, a puzzle that's haunted physics since Schrödinger's day. One explanation, called decoherence, suggests that interactions with the environment, like air molecules or light, collapse superpositions before we notice them. The cat's state is resolved, not by your eyes, but by the universe's constant chatter. Yet this doesn't fully unravel the paradox. It just shifts the mystery, leaving us to wonder where the quantum world ends and ours begins. Take a deep breath. Feel the laboratory's cool air soften into a gentle warmth. The paradox isn't just a theoretical exercise. It's a bridge between physics and philosophy, science and wonder. It's inspired countless debates, from Einstein's skepticism to modern experiments testing alternative interpretations, like the many worlds theory, sidestep the paradox strangeness by suggesting that every quantum event spawns parallel universes. The cosmos stretches before you, a vast tapestry of stars and shadows, each pinprick of light, a story unfolding across billions of years. In the distance, a star's glow bends its path, curving as it passes the immense shadow of a black hole. Space itself warping like a sheet pulled taut. This is the work of gravity, the silent force that holds the universe together, binding planets to stars, stars to galaxies, and you to the earth beneath your feet. It's a force so familiar, you feel it in every step, yet so mysterious, it defies our deepest understanding. Why does gravity exist? And why is it so strangely weak compared to the other forces of nature? This is the enigma of gravity, a concept that lies at the heart of Einstein's revolutionary theories, a riddle that's both a cornerstone of physics and a whisper from the unknown. As you settle into the soothing rhythm of this video, let's drift among the stars, letting gravity's quiet mystery unfold like a celestial tide, guiding your mind toward a restful, contemplative sleep. Gravity is no mere pull. It's a cosmic architect, shaping the universe's structure and challenging our grasp of reality itself. Picture a planet orbiting its star, not because it's tethered by invisible strings, but because the star's mass bends the very fabric of space, creating a dip that the planet rolls through like a marble circling a bowl. This is the vision of Albert Einstein's general theory of relativity, published in 1915, a masterpiece that redefined gravity, not as a force, but as a curvature of space-time. It's a concept so profound, it transformed our understanding of the cosmos. Yet it leaves us with questions that linger like distant stars. Why is gravity so much weaker than the other fundamental forces? What is its true nature, and could it hold the key to secrets beyond our universe? These questions are a bridge between the tangible and the infinite, a puzzle that invites you to ponder the unseen forces that shape your world. Let's drift closer to that black hole, its presence a silent weight in the void. In Einstein's theory, gravity is the result of mass and energy warping spacetime, the four-dimensional fabric that combines space and time. Imagine spacetime as a rubber sheet stretched flat until a massive object, like a star or planet, sits on it, creating a dip. Objects like moons or comets follow the curves of this dip, their paths bending in what we perceive as orbits. This isn't just a metaphor. Experiments have confirmed it. In 1919, during a solar eclipse, astronomers observed starlight bending as it passed near the sun, exactly as Einstein predicted, a triumph that made him a global icon. GPS satellites, ticking slightly faster in weaker gravity, rely on general relativity to stay accurate. A daily reminder that gravity shapes not just the cosmos, but our technology. Yet for all its elegance, Einstein's theory doesn't tell us why gravity exists or why it's so feeble compared to the other forces that govern the universe. Picture yourself floating above that cosmic sheet, the stars glinting like diamonds scattered across a velvet sky. Gravity is one of four fundamental forces in physics, alongside electromagnetism, the strong nuclear force, and the weak nuclear force. Electromagnetism holds atoms together, powers lightning, and drives your phone's circuits. The strong force binds quarks into protons and neutrons, the building blocks of matter. The weak force governs radioactive decay, a quiet player in the universe's chemistry. But gravity? It's the odd one out, 1,000,000 times weaker than electromagnetism. A simple fridge magnet can lift a paperclip against the entire Earth's gravitational pull, a humbling reminder of gravity's faint whisper. This weakness is a mystery, a puzzle that's driven physicists to the edges of theory. If gravity were stronger, stars would collapse into black holes in moments. If weaker, galaxies would never form, and we wouldn't be here to wonder about it. It's as if gravity is perfectly tuned, a delicate thread in the cosmic tapestry. Yet its fragility raises questions that echo through the ages. Take a moment. Let the starlight's gentle glow wrap around you like a soft blanket. The enigma of gravity's weakness has sparked wild ideas, each one a star in the constellation of physics. Some theorists, like those in string theory, propose that gravity might leak into extra dimensions, invisible realms, curled up so tightly we can't perceive them. In our three-dimensional world, gravity seems weak because it's diluted, spreading across dimensions we can't access, like water seeping through a sponge. Others suggest a multiverse, where our universe is one of many, each with different physical laws, and we live in one where gravity's strength is just right for life. These ideas are speculative, beautiful yet untested, like maps to lands we've never seen. They remind us that gravity, for all its familiarity, is a frontier, a mystery that pulls us toward the unknown, asking us to imagine realities beyond our own. Let's drift deeper into the cosmos, the black hole's shadow, now a distant curve. Gravity's history is a saga of human curiosity, from Isaac Newton to Einstein and beyond. Newton, in the 17th century, saw gravity as a universal force, an invisible hand pulling apples to the ground and planets to their orbits. His laws described gravity's effects with stunning precision, guiding us to the moon and beyond. But Newton couldn't explain what gravity was, only how it worked. Einstein took the next leap, weaving gravity into the fabric of space-time, a vision so radical it reshaped physics. His equations predicted phenomena like black holes, regions where gravity is so intense that not even light can escape, and gravitational waves, ripples in spacetime from colliding stars, detected in 2015 by LIGO. These discoveries are like footprints, proof that Einstein's theory holds, yet they deepen the mystery. Why is gravity so different, so weak, so elusive? Imagine yourself orbiting a star, the universe's vastness, a humbling embrace. Gravity's weakness isn't just a curiosity, it's a clue, a hint that our understanding of the universe is incomplete. The other fundamental forces are described by quantum mechanics, a framework where particles and forces interact in precise, probabilistic ways. But gravity resists this framework. Efforts to quantize gravity to find a graviton particle that carries it have faltered, leading to theories like string theory and loop quantum gravity, which propose new ways of seeing the universe. String theory imagines particles as tiny vibrating strings, with gravity emerging from their harmonics, while loop quantum gravity envisions space-time as a web of discrete loops. Both are elegant, unproven, like poems written in a language we're still learning. They suggest that gravity might be a bridge to a deeper truth, a theory of everything that unifies all. Forces a dream physicists chase like sailors seeking a fabled shore. Let's explore what gravity's enigma means for us, how it reshapes our place in the cosmos. Gravity is the force that binds us to the Earth, yet its weakness reminds us of our fragility, our dependence on a delicate balance. It's the force that shaped the universe, sculpting galaxies from gas clouds, yet its mystery hints at realms we can't touch, extra dimensions, parallel universes, or a multiverse where other versions of you ponder the same stars. This duality is what makes gravity so compelling. It's both intimate and infinite, a force we feel in our bones and see in the heavens. It raises questions about our origins, our future, and our place in a universe that might be far stranger than we imagine. What if gravity is a whisper from another reality, a signal from a cosmos beyond our own? It's thought that's both unsettling and comforting, a reminder that we're part of something vast, something we're only beginning to understand. Take a deep breath. Feel the starlight's quiet glow fade into a gentle warmth. Gravity's mystery is a gift, a story that connects you to the cosmos in ways both profound and personal. Every step you take, every breath you draw, is a dance with gravity, a force that's shaped the universe since its first spark. Yet its weakness is a puzzle, a question that invites you to wonder without demanding answers. It's like a melody you can't quite name, but feel in your bones, a lullaby for the curious mind. As you lie there, your body sinking into the mattress, let gravity's enigma be a guide, a soft pull leading you into the night. There's no need to solve the riddle tonight, or ever. It's enough to feel its weight, to let its quiet awe cradle your thoughts as you drift toward dreams. The debate around gravity is a cosmos of its own, filled with voices chasing its secrets. Some physicists, like Lisa Randall, explore extra dimensions, imagining gravity's strength diluted across unseen realms. Others, like Juan Maldacena, probe string theory's holographic ideas, where gravity emerges from a deeper two-dimensional reality. There's no consensus, no final equation to pin it down. Gravity's enigma endures, a testament to its power to provoke and inspire. It's a puzzle that doesn't demand resolution, but contemplation, a perfect star to guide us through the night. This tale of gravity's cosmic curves is just one light in the constellation of physics concepts we're exploring tonight. Each will illuminate another facet of the universe, revealing the strange, beautiful truths that shape our reality. From gravity's silent pull, we'll drift to a realm where time itself stretches and slows, a phenomenon that warps our sense of now. Picture a spaceship racing near the speed of light, its crew aging slower than those left behind. What does it mean for time to bend? Close your eyes, let the stars glow, fade into the quiet hum of a distant engine, and let's drift into the next mystery, where time begins to unravel. The stars shimmer above a cosmic sea, stretching beyond the horizon, their light a quiet promise of journeys yet to come. You are standing on the deck of a spaceship, its sleek hull humming with energy, ready to launch into the vastness of space. As the engines roar, you accelerate faster and faster, approaching the speed of light, the universe blurring into streaks of brilliance. But then, you return to Earth, stepping onto familiar soil, only to find your friends and family aged decades, their faces lined with years, while you barely changed, your reflection in the mirror, untouched by time. This is time dilation, a mind-bending prediction of Einstein's theory of relativity, a phenomenon that reveals time as fluid, not fixed, bending with speed and gravity. It's a concept that challenges our deepest assumptions about the present, a riddle that asks, if time can stretch and slow, what is now? As you settle into the soothing rhythm of this video, let's drift through the cosmos, letting time dilation's gentle mystery unfold like a starlit dream, guiding your mind toward a restful, contemplative sleep. This isn't just a quirk of physics. It's a window into the universe's strange architecture, but truth so profound it reshapes our understanding of reality itself. Imagine time as a river, its current steady in our daily lives, ticking away in seconds, minutes, hours. We trust its flow, counting on it to carry us from breakfast to bedtime, from youth to age. But Einstein's relativity, unveiled in the early 20th century, shows that this river can meander slow or rush, depending on where you stand in the cosmos. Time dilation tells us that time isn't universal. It stretches for those moving near the speed of light or dwelling in strong gravitational fields, while others age at a different pace. It's a concept that's both scientific and deeply human, touching on our dreams of exploration, our fears of loss, and our longing to hold on to moments that slip away. As you lie there, your breath slow and even, let's board that spaceship, soaring into a paradox that bends time itself, inviting you to ponder the fleeting nature of now. Let's launch into the stars, the spaceship's engines a low hum beneath your feet. Time dilation comes in two flavors, both rooted in Einstein's theories of relativity. The first, from Special Relativity published in 1905, deals with motion. It says that time slows for objects moving close to the speed of light, 299,792,458 meters per second, relative to a stationary observer. If you're on a spaceship racing at 90% of light speed, time for you crawls compared to someone back on Earth. A year aboard the ship might equal decades on the ground, a phenomenon called the twin paradox. Imagine twins, one staying home, the other rocketing through space. When the traveler returns, they're younger, their sibling now gray and weathered, as if time played favorites. It's not magic, it's physics, confirmed by experiments like those with atomic clocks on fast-moving planes, ticking slightly slower than their earthbound counterparts. Picture yourself aboard that spaceship, the stars streaking past like fireflies in a cosmic wind. The math behind time dilation is elegant, rooted in the Lorentz factor, a formula that shows time stretching as speed increases. At everyday speeds, the effect is negligible. Your car's dashboard clock doesn't lag on the highway. But near light speed, the difference is dramatic. If you traveled at 99.9% of light speed for a year, decades might pass on Earth. Your life, a fleeting moment against the world's turning. It's as if time is a rubber band stretching for the traveler, snapping back for those left behind. This isn't science fiction. Muons, subatomic particles zipping through the atmosphere, live longer than expected because their high speeds dilate their internal clocks. a real-world echo of the twin paradox. Let's drift deeper into the cosmos. The spaceship's hum, a soothing pulse. The second flavor of time dilation comes from general relativity, Einstein's 1915 masterpiece, which describes gravity as the curvature of spacetime. In strong gravitational fields like near a black hole, time slows compared to weaker fields. A clock on a mountaintop ticks faster than one at sea level, where Earth's gravity is stronger. The difference is tiny but measurable, as seen in GPS satellites which orbit in weaker gravity and must adjust their clocks to sync with Earth. Imagine standing near a black hole, its immense gravity warping time so profoundly that minutes for you are years for someone far away. It's like living in a slow-motion world where the universe races ahead while you linger caught in gravity's embrace. Take a moment. Let the starlight's gentle glow wrap around you like a soft veil. Time dilatation's implications are profound, challenging our intuitive sense of a universal now. In our daily lives, we assume time is the same everywhere. A meeting at 3 p.m. is 3 p.m. for everyone, but relativity shows that now is relative, fragmented across the cosmos. If you're on a speeding spaceship, your now drifts out of sync with Earth's now, creating a temporal gap that grows with distance and speed. Near a black hole, your now could be centuries apart from a distant observer's. It's as if the universe is a symphony, each player following a different tempo, yet somehow harmonizing into the reality we know. This fragmentation raises questions about connection, about how we share moments across a cosmos where time bends and stretches. Let's linger aboard the spaceship, the stars now a quiet hum in your mind. Time dilation's roots trace back to Einstein's genius, a leap that unified space and time into a single malleable fabric. Special relativity, born from thought experiments about light and motion, showed that nothing can exceed light speed, a cosmic limit that ties time dilation to the universe's structure. General relativity expanded this, weaving gravity into the equation, predicting phenomena like gravitational lensing, where starlight bends around massive objects, confirmed during a second paragraph. 1919 solar eclipse. These theories aren't just abstract, they're practical. Without correcting for time dilation, GPS would fail navigation systems, drifting off course. It's a reminder that the strangest corners of physics touch our lives, from satellites to smartphones, grounding the cosmic in the everyday. Imagine yourself gazing out the spaceship's window, the universe a canvas of light and shadow. Time dilation's implications stretch beyond. If time varies, what does that mean for aging, for memory, for the moments we cherish? The twin paradox isn't just a thought experiment. It's a story of separation, of one sibling living a lifetime while another stays young. It echoes our fears of losing time, of watching loved ones age while we're apart, whether by distance or circumstance. In science fiction, time dilation fuels tales of explorers returning to a changed world, their home transformed while they lingered in the stars. It's a concept that resonates with our longing to hold on to time, to slow its relentless march. Yet it reminds us that time is a river flowing differently for each of us. Let's explore the paradox's broader ripples. The stars now a gentle pulse in the night. Time dilation challenges our sense of a shared reality, raising questions about causality and connection. If your now differs from mine, how do we define events across the cosmos? Astronomers observing distant galaxies see light from billions of years ago, a now that's long past. In a relativistic universe, simultaneity is an illusion, a truth that's both humbling and awe-inspiring. It suggests that our perception of time is just one perspective, a single thread in a cosmic tapestry. Philosophers like Immanuel Kant argued that time is a human construct, a way we order experience, and relativity seems to agree, showing time as malleable, shaped by speed and gravity. What if our sense of time is just a shadow of a deeper truth, a glimpse of a universe where past, present, and future blur? Take a deep breath. Feel the spaceship's hum fade into a quiet warmth. Time dilation also sparks dreams of exploration, of reaching distant stars within a human lifetime. If you could travel near light speed, you might visit a planet centuries away, returning to find Earth transformed, your journey a mere moment in your life, but an era in theirs. It's a tantalizing possibility, yet a poignant one, a reminder that exploration comes with sacrifice. The concept fuels debates about interstellar travel, with physicists like Kip Thorne exploring ideas like wormholes to bypass time's barriers. Yet time dilatation's reality is already here, in the muons that outlive their expected lifespans, in the clocks that tick faster in orbit. It's a truth woven into the universe, a melody that plays whether we hear it or not. Let's linger in the stars, the cosmos now a soft glow in your mind. The debate around time dilation is a constellation of voices, from Einstein's peers who marveled at his insights, to modern physicists testing relativity's limits. Experiments like those with particle accelerators confirm time dilation's effects, while gravitational wave detections validate general relativity's predictions. Some, like string theorists, seek a quantum theory of gravity that might unify time dilation with the subatomic world, a dream still out of reach. There's no final answer, only a deepening mystery that invites wonder. Time dilation's power lies in its ability to provoke without resolving, a perfect puzzle for quiet reflection as you drift toward sleep. Picture the spaceship one last time, its hull glinting in the starlight, a vessel carrying you through time's shifting currents. Time dilation is a gift, a story that challenges your mind while calming your soul. It reminds us that time is not a chain, but a river flowing differently for each traveler, yet binding us all in its cosmic dance. As you lie there, your body sinking into the mattress, let the paradox be a lullaby, its rhythm soothing your thoughts into a gentle haze. There's no need to grasp time tonight. It's enough to ponder it, to let its quiet mystery wrap around you like a dream, guiding you toward peace. This tale of time's stretching threads is just one light in the constellation of physics concepts we're exploring tonight. Each will illuminate another facet of the universe, revealing the strange, beautiful truths that shape our reality. From time dilation's cosmic rhythm, we'll drift to a realm where certainty itself dissolves, where a particle's secrets defy our grasp. Picture an electron flitting through the void, its path a mystery we can't pin down. What does it mean to know the unknowable? Close your eyes. Let the spaceship's hum fade into the quiet buzz of a subatomic world And let's drift into the next mystery, where uncertainty begins to reign. The universe hums with a quiet energy, a subatomic dance unfolding in the spaces too small to see. Picture an electron, a fleeting speck of matter zipping through the void, its path a whisper of possibility. You try to pin it down, to know exactly where it is and how fast it's moving, but the more you focus on one, the other slips away, like a melody whose notes blur when you listen too closely. This is the Heisenberg uncertainty principle, a cornerstone of quantum mechanics proposed by Werner Heisenberg in 1927, a law that reveals a universe where certainty is an illusion, where the act of knowing one truth obscures another. It's not just a technical quirk, it's a paradox that challenges our deepest desire for precision, a riddle that asks, if the universe is built on uncertainty, what can we truly know? As you settle into the soothing rhythm of this video, let's drift into this quantum realm, letting the principle's gentle mystery unfold like a shadow in the void, guiding your mind toward a restful, contemplative sleep. This isn't a mere footnote in physics, it's a revolution, a truth that upends our classical view of a predictable, clockwork universe and replaces it with a reality of probabilities and flux. Imagine trying to catch that electron, to map its journey with the precision of a cartographer charting a river. In the world of Isaac Newton, you could know both its position and speed, plotting its path like a ball rolling down a hill. But in the quantum world, Heisenberg tells us this is impossible. The more precisely you measure the electron's position, the less you know about its momentum and vice versa. It's not a flaw in our tools or a limit of our technology. It's a fundamental property of nature woven into the fabric of reality itself. This principle is a window into the strange subatomic realm where the rules we take for granted dissolve, leaving us to ponder a universe that's both familiar and utterly alien. As you lie there, your breath slow and even, let's chase that electron through the quantum fog, exploring a paradox that reshapes our understanding of existence. Let's step into the quantum realm, the air alive with the buzz of unseen particles. The Heisenberg uncertainty principle is rooted in the wave-particle duality of quantum mechanics, a discovery that emerged in the early 20th century as scientists probed the building blocks of matter. Particles like electrons don't behave like tiny marbles. They act as both particles and waves, their properties spread out like ripples on a pond. When you measure an electron's position, you're pinning down a specific point, collapsing its wave-like nature into a single spot. But this act disrupts its momentum, the wave's motion blurring into uncertainty. It's like trying to capture a song's exact note and rhythm at the same moment. One sharpens while the other fades. Heisenberg quantified this trade-off with a simple equation. The product of the uncertainties in position and momentum is always at least a small constant, a limit set by Planck's constant, the quantum world's fundamental unit. Picture yourself in laboratory, its walls lined with humming machines, a screen flickering with the ghostly paths of particles. The principle's discovery was a seismic shift, born in the 1920s, when quantum mechanics was rewriting physics. Heisenberg, a young German physicist, was grappling with the strange behavior of atoms, guided by mentors like Niels Bohr and Max Born. In 1927, he realized that measurement itself alters the quantum state, a revelation that shook the foundations of classical physics. Before Heisenberg, scientists believed the universe was deterministic. Know the position and velocity of every particle, and you could predict the future forever. But the uncertainty principle says no. At the quantum level, there is an inherent fuzziness, a limit to what we can know. It's as if the universe is playing a cosmic game of hide and seek, revealing only parts of itself, keeping the rest veiled in shadow. Take a moment. Let the laboratory's hum fade into a gentle pulse. The principle's implications are profound, reaching far beyond the subatomic. It challenges our dream of a fully knowable universe, suggesting that reality is probabilistic, not certain. If you can't know both an electron's position and momentum, you can't predict its exact path, only the likelihood of where it might go. This uncertainty cascades upward, shaping the behavior of atoms, molecules, and it's the reason we describe quantum systems with wave functions, mathematical clouds of probability that tell us where a particle is likely to be. It's like forecasting the weather. You can predict rain, but not the exact path of every drop. This probabilistic view, formalized by Born, became the bedrock of quantum mechanics, a framework that's led to technologies like transistors, lasers, and MRI machines, all born from the principle's strange truth. Let's drift deeper into the quantum fog. The electron's path, now a faint shimmer in your mind. The Heisenberg uncertainty principle isn't just about measurement. It's about the nature of reality itself. When you measure a particle's position, you interact with it, sending a photon or another particle to probe its state. This interaction disturbs the particle, altering its momentum in unpredictable ways. It's not a technical limitation, but a fundamental one, rooted in the quantum world's wave-like nature. Heisenberg's insight was that this uncertainty is intrinsic, not something we can engineer away. It's as if the universe has a built-in blur, a limit to its sharpness, like a painting whose details smudge when you look too closely. This realization was a shock to physicists like Albert Einstein, who famously argued that God does not play dice, insisting there must be hidden variables determining a particle's state. But experiments like those testing Bell's inequalities have confirmed quantum mechanics predictions, showing that uncertainty is real, not a gap in our knowledge. Imagine yourself watching that electron, its wave-like form rippling through the void. The principle's implications stretch into philosophy, challenging our ideas about knowledge and control. If the universe is inherently uncertain, what does that mean for determinism, the belief that every event is fixed by prior causes? Quantum mechanics suggests a world where chance plays a role, where outcomes are probabilities, not certain. This has sparked debates about free will. Could quantum uncertainty give us a sliver of freedom in a universe of cause and effect? Philosophers like David Bohm propose deterministic alternatives, but the mainstream view, backed by experiment, embraces uncertainty as a core feature of reality. It's a humbling thought, isn't it? The idea that the universe, at its deepest level, resists our need for absolute answers, offering instead a tapestry of possibilities. Let's explore the principle's broader ripples. The laboratory, now a quiet hum in your mind. The Heisenberg uncertainty principle has practical impacts, shaping the technologies that define our world. Quantum tunneling, where particles borrow energy to pass through barriers, relies on uncertainty, enabling processes like nuclear fusion in stars and scanning tunneling microscopes on Earth. Quantum cryptography uses uncertainty to secure data, ensuring that any eavesdropping disrupts the system, a real-world application of Heisenberg's insight. The principle also underpins the uncertainty in energy and time, another quantum limit that allows particles to pop into existence briefly, a phenomenon central to theories like the Big Bang's inflationary phase. It's a reminder that uncertainty isn't a flaw, but a feature, a creative force that drives the universe's evolution. Picture the electron again, its path a ghostly flicker in the void. The principle's history is a saga of human curiosity, born in the 1920s, when quantum mechanics was a radical new science. Heisenberg, barely 26, was wrestling with the mathematics of atomic spectra, guided by Bohr's Copenhagen school. His insight came in a burst of clarity, formalized in a 1927 paper that stunned the physics world. Einstein resisted, sparking debates that continue today, while Bohr embraced uncertainty as a new paradigm. The principle's name became synonymous with quantum mechanics' strangeness, inspiring both awe and skepticism. Experiments like those with single photons have confirmed its predictions, showing that uncertainty is not a theory, but a fact woven into the universe's fabric. Let's linger in the quantum realm. The electrons shimmer, now a soft glow in your mind. The principle also touches on human experience, echoing our own struggles with certainty. In life, we seek clarity, where to go, who to love, what to believe, but often find ourselves balancing trade-offs, knowing one thing at the cost of another. The uncertainty principle is a cosmic mirror reflecting this human truth. To know is to choose, and every choice leaves something unknown. It's a comforting thought, isn't it? The idea that uncertainty is not a failure, but a part of existence, a rhythm that pulses through both particles and people. As you lie there, your body sinking into the mattress, let the principle be a lullaby, its rhythm soothing your thoughts into a gentle haze. There's no need to pin down the electron tonight. It's enough to ponder it, to let its quiet mystery wrap around you like a dream, guiding you toward peace. The debate around the Heisenberg uncertainty principle is a laboratory of its own, filled with voices seeking to unravel its meaning. Some, like Einstein, sought hidden variables to restore determinism, but tests like Bell's theorem have largely ruled them out. Others, like John Wheeler, embraced uncertainty as a creative force, suggesting it shapes the universe's participatory nature. There's no final answer, only a deepening mystery that invites wonder. The principle's power lies in its ambiguity, its ability to provoke without resolving, a perfect puzzle for quiet reflection as you drift toward sleep. This tale of quantum uncertainty is just one light in the constellation of physics concepts we're exploring tonight. Each will illuminate another facet of the universe, revealing the strange, beautiful truths that shape our reality. From the Heisenberg uncertainty principle, with its dance of probabilities, we'll drift to a realm where particles connect across vast distances, defying the limits of space. Picture two particles light years apart, yet bound in a spooky embrace. What does it mean for the universe to be so entwined? Close your eyes, let the laboratory's buzz fade into the quiet hum of a cosmic bond. And let's drift into the next mystery, where entanglement begins to weave its spell. The cosmos hums with a silent pulse, a vast tapestry of stars and shadows stretching beyond the reach of imagination. In this infinite expanse, two particles, mere specks of matter, float light-years apart, separated by gulfs of space that defy comprehension. Yet they are bound, connected in a way that mocks distance, as if sharing a secret whispered across the universe. Touch one, measure its spin or position, and the other responds instantly, its state shifting in perfect harmony, no matter how far apart they are. This is quantum entanglement, a phenomenon so strange that Albert Einstein called it spooky action at a distance, a riddle that defies our understanding of space, time, and connection. It's not just a quirk of physics, it's a paradox that suggests the universe is woven together in ways we're only beginning to grasp. A mystery that asks, what does it mean for reality to be so deeply entwined? As you settle into the soothing rhythm of this video, let's drift among the stars, letting entanglement's gentle enigma unfold like a cosmic thread, guiding your mind toward a restful, contemplative sleep. This isn't a mere scientific oddity, it's a cornerstone of quantum mechanics, a truth that challenges the very fabric of reality and opens doors to dreams of technology and philosophy alike. Imagine those two particles, perhaps electrons or photons, born together in a fleeting moment of interaction, their fates intertwined forever. When you measure one, its partner, no matter how distant, mirrors the result, as if they're dancing to the same silent tune. It's a connection that seems to defy the speed of light, the ultimate cosmic speed limit, suggesting a deeper unity beneath the universe's surface. Entanglement is more than a puzzle. It's a whisper from the quantum realm, hinting at a reality where separation is an illusion, where the cosmos is a single interconnected whole. As you lie there, your breath slow and even, let's follow those particles across the stars, exploring a paradox that binds the universe in ways both strange and beautiful. Let's drift into the quantum realm, the air alive with the quiet buzz of unseen particles. Quantum entanglement occurs when two or more particles interact in a way that links their quantum states, creating a shared destiny. Once entangled, their properties, like spin, position, or polarization, are correlated no matter how far apart they drift. Measure one particle's spin, and the other's spin is correlated, instantly determined, even if it's on the other side of the galaxy. This isn't a signal traveling between them. Nothing moves faster than light. Instead, it's as if the particles share a single quantum state, a ghostly bond that transcends space. It's like rolling two dice, one on Earth, one near a distant star, and finding they always land on matching numbers every time, without any apparent communication. This phenomenon, first theorized in the 1930s, has been confirmed by countless experiments, yet its meaning remains a cosmic mystery. Picture yourself in a laboratory, its walls lined with gleaming equipment, a screen flickering with the dance of entangled particles. The concept of entanglement emerged from the early days of quantum mechanics, a revolutionary field born in the 1920s. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper, the famous EPR paper, arguing that quantum mechanics was incomplete. They proposed a thought experiment involving entangled particles, suggesting that if two particles could influence each other instantly across vast distances, it implied spooky action that violated the rules of relativity. Einstein believed there must be hidden variables, unseen factors determining the particle's states, preserving a deterministic universe. But in 1964, physicist John Bell devised a way to test this, creating inequalities that could distinguish between quantum. Experiments starting in the 1970s with physicists like John Clauser and Elaine Aspect confirmed quantum mechanics entanglement is real, and no hidden variables explain it. It's as if the universe is playing a game with rules we don't yet understand. Take a moment. Let the laboratory's hum fade into a gentle cosmic pulse. The implications of quantum entanglement are profound, reshaping our view of space and connection. In classical physics, objects are separate, their interactions limited by distance and the speed of light. But entanglement suggests a deeper unity, a non-locality where space isn't the barrier we think. When you measure one entangled particle, its partner's state collapses instantly, no matter the distance, 10 meters or 10 billion light years. This doesn't violate relativity, as no information travels faster than light, but it challenges our intuitive sense of locality, the idea that events are only influenced by their immediate surroundings. It's like two dancers, galaxies apart, moving in perfect sync, without a signal, as if the universe itself is their choreographer. This non-locality raises questions about the nature of reality. Is the universe a collection of separate pieces or a single, interconnected whole? Let's drift deeper among the stars, the particles' bond, a faint shimmer in your mind. Entanglement's implications stretch into technology, fueling dreams of a quantum revolution. Quantum computers, still in their infancy, use entangled particles to perform calculations far beyond classical. Machines solving problems like code breaking or drug design in moments. Quantum cryptography leverages entanglement to create unbreakable codes, where any attempt to eavesdrop disrupts the system. A security rooted in the universe's own laws. Teleportation, in a sense, is already real. Scientists have teleported quantum states between entangled particles, not moving matter, but transferring information instantly. These applications are like seed. Yet they also deepen the mystery. Why does the universe allow such connections, and what does it mean for our place in it? Imagine yourself floating in the cosmic void, the stars, a quiet choir above. Entanglement's philosophical implications are as vast as the universe itself. It suggests a reality where separation is an illusion, where every particle is potentially linked to every other, a cosmic web of connections. Some physicists, like David Bohm, proposed a holographic universe where entanglement reflects a deeper, unified order, like a hologram where each part contains the whole. Others, like philosopher Tim Maudlin, argue that entanglement challenges our understanding of causality, suggesting the universe operates by rules we can't yet grasp. It's a humbling thought, isn't it? The idea that the cosmos might be a single entwined entity, with you, me, and the stars, all threads in the same tapestry. It raises questions about individuality, about what it means to be separate in a universe that's so deep. Let's explore entanglement's broader ripples, the laboratory now a distant memory in the starlit void. The phenomenon has sparked debates that echo through science and philosophy. Einstein's skepticism led to Bell's inequalities, which experiments have consistently upheld, ruling out local hidden variables. Yet some physicists, like those in the many worlds interpretation, suggest entanglement reflects branching universes, where every measurement creates new realities. Others explore entanglement's role in black holes with theories like the ER-EPR conjecture, proposing that entangled particles are linked by tiny wormholes, bridges in spacetime. These ideas are speculative, beautiful, like poems written in starlight. Yet they remind us that entanglement is a frontier, a clue to a deeper truth about the universe. Picture the two particles again, their bond a faint glow across the cosmos. Entanglement's history is a saga of human curiosity, from the EPR paper's challenge to Bell's groundbreaking tests. In the 1980s, Aspect's experiments with entangled photons showed correlations that defied classical physics, cementing entanglement's reality. Recent advances, like quantum teleportation over hundreds of kilometers, push the boundaries further, making entanglement a cornerstone of the quantum age. Yet its meaning remains elusive, a riddle that invites both awe and humility. It's as if the universe is whispering a secret, one we can hear but not yet fully understand, a melody that plays through every particle, every star. Let's linger in that starlight, the particles' connection, now a soft hum in your mind. Entanglement also touches human experience, echoing our own longing for connection. We seek bonds, friends, family, lovers that transcend distance, that feel instantaneous, unbreakable. Entanglement is a cosmic mirror reflecting this desire, suggesting that connection is woven into the universe's fabric. It's a comforting thought, isn't it? The idea that even in the vastness of space, nothing is truly L. As you lie there, your body sinking into the mattress, let entanglement be a lullaby, its rhythm soothing your thoughts into a gentle haze. There's no need to unravel the bond tonight. It's enough to ponder it, to let its quiet mystery wrap around you like a dream, guiding you toward peace. The debate around entanglement is a cosmos of its own, filled with voices seeking its truth. Some, like physicist Anton Zeilinger, push experimental boundaries, entangling particles across ever greater distances. Others, like Juan Maldacena, explore theoretical links to spacetime. Itself, there's no final answer, only a deepening mystery that invites wonder. Entanglement's power lies in its ambiguity, its ability to provoke without resolving, a perfect puzzle for quiet reflection as you drift towards sleep. This tale of cosmic connection is just one light in the constellation of physics concepts we're exploring tonight. Each will illuminate another facet of the universe, revealing the strange, beautiful truths that's is. From quantum entanglement's spooky bonds, we'll drift to a theory where every choice spawns a new universe, a reality that branches into countless worlds. Picture a single quantum event splitting the cosmos into parallel paths. What does it mean to live in a multiverse? Close your eyes. Let the starlight's hum fade into the quiet pulse of infinite realities. And let's drift into the next mystery, where the universe begins to multiply. The universe hums with a silent rhythm, a vast tapestry of stars and possibilities stretching beyond the grasp of imagination. Picture a single moment, a fleeting choice, perhaps a particle spinning left or right, or a decision you made today, like turning left instead of right at a crossroad. Now imagine that choice splitting reality itself, spawning new universes where every possible outcome plays out. In one world, the particle spins left. In another, it spins right. In one reality, you turned left. In another, you turned right. Each path unfolding a different life, different cosmos. This is the many worlds interpretation of quantum mechanics, a mind-bending theory proposed by physicist Hugh Everett in 1957, a vision that suggests our reality is just one thread in an infinite tapestry of branching worlds. It's a paradox that challenges our sense of singularity, asking, if every choice creates a new universe, who are we in this cosmic multitude? As you settle into the soothing rhythm of this video, let's drift through this multiverse, letting the theory's gentle mystery unfold like a starlit dream, guiding your mind toward a restful, contemplated sleep. This isn't just a theoretical curiosity, it's a revolution in how we view reality. A concept that takes the strange probabilities of quantum mechanics and weaves them into a cosmos of endless possibilities. Imagine reality as a tree, its trunk the universe at its birth, each quantum event a branch splitting into new paths, each path a universe with its own stars, planets, and versions of you. Unlike the Copenhagen interpretation, where quantum possibilities collapse into one outcome when observed, the many worlds interpretation says no collapse occurs. All outcomes happen, each in a separate parallel universe. It's a vision that's both exhilarating and disorienting, suggesting that every moment is a crossroads, every choice a new world. It's a theory that bridges physics and philosophy, touching on identity, fate, and the nature of existence itself. As you lie there, your breath slow and even, let's step into this branching cosmos, exploring a paradox that multiplies reality into infinity. Let's drift into the quantum realm, the air shimmering with the hum of unseen possibilities. The many worlds interpretation was born to address a puzzle at the heart of quantum mechanics, the measurement problem. In the quantum world, particles like electrons exist in superpositions, multiple states at once, spinning left and right, or being in two places until measured. The Copenhagen interpretation, dominant in the 1920s, says measurement collapses this superposition into one state, like a cosmic coin toss, settling on heads or tails. But why does it collapse, and what chooses the outcome? Hugh Everett, a young physicist at Princeton, proposed a radical alternative. There's no collapse. Instead, every possible outcome occurs, each in a new universe. When you measure an electron's spin, reality splits one universe where it's left, another where it's right, and you, the observer, split too, each version seeing a different result. It's like a choose-your-own-adventure book, where every ending is real, each page a new world. Picture yourself in a laboratory, its walls lined with flickering screens, a quantum experiment unfolding before you. The electron is fired, its spin measured, and the universe branches. In one reality, the screen shows left, in another, right. You're there in both, unaware of the other. You, each convinced their world is the only one. This is the essence of many worlds. No probabilities are discarded, no possibilities lost. The theory's elegance lies in its simplicity. It takes quantum mechanics at face value, letting the math of wave functions dictate reality, without adding mysterious collapses. Everett's idea, published in 1957, was initially met with skepticism, dismissed by giants like Niels Bohr. But over decades, it gained traction, championed by physicists like Bryce DeWitt and David Deutsch, who saw it as a bold solution to quantum's deepest puzzle. It's a vision that feels like a cosmic symphony, each note a new universe, playing in harmony forever. Take a moment. Let the laboratory's hum fade into a gentle cosmic pulse. The implications of many worlds are staggering, reshaping our sense of reality and self. If every quantum event spawns a new universe, the number of worlds is unimaginable, trillions upon trillions, each differing by a single particle's choice, each as real as ours. In some, you're an astronaut, soaring among the stars. In others, you never left your hometown. In some, the Earth thrives. In others, it's a barren wasteland. It's as if every possibility, every what-if, is real somewhere, a cosmic library where every story is written. This multiplicity challenges our notion of a single unique reality, raising questions about identity. If countless versions of you exist, who is the real you? Are you just one thread in an infinite tapestry, or something more? Let's drift deeper into the multiverse, the stars now a shimmering web of worlds. The many worlds interpretation doesn't just multiply universes, it redefines observation itself. In Copenhagen, the act of measuring collapses the wave function, but in many worlds, measurement is just a splitting, a moment where you and the universe branch into new paths. It's a deterministic view. Strangely enough, every outcome is fixed by the quantum state, with no randomness, only the illusion of chance from your perspective. In one branch, this determinism is both comforting and unsettling, like knowing every choice you make is mirrored by countless others, each version of you living a different truth. It's a paradox, because it preserves all possibilities, yet leaves you anchored in one, unaware of the others. A single note in a symphony you'll never hear in full. Imagine yourself standing at a cosmic crossroads, each path a new universe, each step a new you. The theory's roots trace back to Everett's 1957 dissertation, a bold challenge to the Copenhagen orthodoxy. At the time, quantum mechanics was still young, its pioneers wrestling with its strange implications. Everett's advisor, John Wheeler, supported the idea, but urged caution, fearing it was too radical. The physics community largely ignored it, favoring Copenhagen's simplicity. But by the 1970s, interest grew, driven by experiments like those testing Bell's inequalities, which confirmed quantum mechanics' predictions. Many worlds offered a way to explain these without invoking collapses, appealing to physicists like Deutsch, who saw it as a framework for quantum computing. It's a theory that's gained a cult following, inspiring science fiction and philosophy, yet remains unproven. A cosmic hypothesis that's as beautiful as it is elusive. Let's explore the theory's broader ripples. The laboratory, now a distant memory in the starlit void. Many worlds has practical implications, particularly in quantum computing, where the idea of parallel computations mirrors the branching of universes. Deutsch argued that quantum computers tap into these parallel worlds, performing calculations across multiple realities, a tantalizing possibility that fuels research today. The theory also influences cosmology, with some suggesting our universe's fine-tuned constants, like gravity's strength, make sense in a multiverse where every variation exists. It's like rolling cosmic dice, infinitely landing on a world where life can thrive. Yet the theory's untestability is its Achilles heel. How do you prove other universes exist if they're unreachable? Critics like physicist Sabine Hossenfelder picture yourself drifting through the multiverse. Each star, a new world. Each light, a new you. The theory's philosophical implications are profound, touching on identity, morality, and destiny. If every choice creates a new universe, what does that mean for free will? Are you free if every option is taken somewhere? It's a liberating thought, suggesting every dream you didn't pursue lives on in another reality. Yet it's also disorienting, diluting the uniqueness of your path. Ethically, it raises questions. If harm happens in one world but not another, does it matter? Philosophers like David Lewis, with his modal realism, echo many worlds, imagining all possible worlds as real, a framework that blends physics with metaphysics. It's as if the universe is a cosmic novel, every chapter written, every ending true. Let's linger in the starlight. The multiverse, now a soft glow in your mind. Many worlds also resonates with human experience, echoing our own what-ifs. We all wonder about paths not taken, different careers, loves, lives. The theory is a cosmic mirror, reflecting this longing, suggesting those paths exist, each as real as the one you're on. It's a comforting thought, isn't it? The idea that every version of you is out there, living every possibility, a symphony of selves playing in harmony. As you lie there, your body sinking into the mattress, let many worlds be a lullaby, its rhythm soothing your thoughts into a gentle haze. There's no need to choose a single path tonight. It's enough to ponder them, to let their quiet mystery wrap around you like a dream, guiding you toward peace. The debate around many worlds is a cosmos of its own, filled with voices seeking its truth. Supporters like physicist Sean Carroll argue it's the simplest interpretation, faithfully following quantum mechanics math. Critics like Roger Penrose doubt its plausibility, citing the immense complexity of infinite universes. There's no consensus, only a deepening mystery that invites wonder. The theory's power lies in its ambiguity, its ability to provoke without resolving, a perfect puzzle for quiet reflection as you drift towards sleep. This tale of branching worlds is just one light in the constellation of physics concepts we're exploring tonight. Each will illuminate another facet of the universe, revealing the strange, beautiful truths that shape our reality. From the many worlds interpretation, with its infinite tapestry of realities, we'll drift to a cosmic mystery where matter hides in darkness, shaping the universe unseen. Picture galaxies spinning, held by an invisible force we can't touch. What is this shadow that binds the cosmos? Close your eyes. Let the multiverse's glow fade into the quiet pull of an unseen presence, and let's drift into the next mystery, where dark matter begins to whisper. The night sky unfurls above a vast canvas of stars and galaxies, each pinprick of light a beacon in the cosmic dark. Yet as you gaze, you sense an unseen presence, a silent force holding these swirling spirals together, keeping stars from flying apart like leaves in a storm. This is dark matter, a mysterious substance that weaves through the universe, shaping its structure without ever revealing itself. It doesn't glow, doesn't absorb light, yet its gravitational pull binds galaxies, sculpting the cosmos into the intricate tapestry we see. Estimated to make up 27% of the universe's mass energy, dark matter is one of physics' greatest enigmas, a shadow that's everywhere and nowhere, a riddle that asks, what is this invisible force that holds the universe's secrets? As you settle into the soothing rhythm of this video, let us drift among the galaxies, letting dark matter's quiet mystery unfold like a whisper in the void, guiding your mind toward a restful, contemplative sleep. This isn't just a scientific puzzle, it's a cosmic detective story, a quest to understand a substance that's as essential to the universe as stars, yet remains maddeningly elusive. Imagine galaxies spinning their outer stars, moving faster than gravity, from visible matter. Stars, gas, dust should allow. Without something extra, these galaxies would unravel their stars, flung into the void. That something is dark matter, inferred not because we see it, but because we see its effects. Like footprints in the sand, with no walker in sight. It's a concept that challenges our understanding of the cosmos, suggesting that much of reality is hidden beyond our senses, yet shaping every structure we know. Why does dark matter exist, and what is it made of? These questions are a bridge between the tangible and the unknown, a mystery that pulls us into the heart of the universe's unseen architecture. As you lie there, your breath slow and even, let's chase this invisible force through the stars, exploring a paradox that binds the cosmos in silence. Let's drift into the galactic void, the air shimmering with the hum of unseen forces. Dark matter's presence is deduced from its gravitational influence, a discovery rooted in the 20th century's growing understanding of the cosmos. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma Cluster, a group of galaxies moving so fast that their visible mass couldn't hold them together. He proposed missing mass, an invisible substance exerting extra gravity, but his idea was largely ignored. Decades later, in the 1970s, American astronomer Vera Rubin observed galaxy rotation curves, finding that stars at a galaxy's edge moved as fast as those near the center, defying expectations. Something unseen was providing the gravitational glue, and Rubin's work, built on Zwicky's, cemented dark matter's place in cosmology. It's like hearing a melody, but never seeing the musician. Knowing the music is there because it fills the air. Picture yourself orbiting a galaxy, its spiral arms glowing like a cosmic pinwheel. Dark matter's effects are everywhere, not just in galaxy rotation. It shapes galaxy clusters, bending light from distant stars through gravitational lensing, creating arcs and distorted images that astronomers map with telescopes like Hubble. It influences the cosmic microwave background, the Big Bang's afterglow, leaving subtle patterns that satellites like Planck have measured. These are like fingerprints, proof of dark matter's role in the universe's infancy, helping gas clouds collapse into the first stars. Yet for all its influence, dark matter remains invisible. It doesn't emit or absorb light, doesn't form stars or planets, and doesn't interact with normal matter except through gravity. It's as if the universe has a shadow self, a silent partner that shapes its dance without ever stepping into the light. Take a moment. Let the galaxy's glow fade into a gentle hum. The nature of dark matter is one of physics' deepest mysteries, a puzzle that sparked a flurry of theories. The leading candidate is weakly interacting massive particles, or WIMPs, hypothetical particles that exert gravity and interact weakly with normal matter, passing through us like ghosts. Experiments like those in deep underground labs, such as the Large Underground Xenon Detector, search for WIMPs by watching for rare collisions with atoms. But so far, they found nothing conclusive. Other theories propose axions, ultralight particles that might form a cosmic fog, or massive compact halo objects, machos, like rogue planets or dead stars. Some even suggest modifying gravity itself, with theories like modified Newtonian dynamics, MOND, though these struggle to explain all observations. It's like chasing a phantom, each clue leading to more questions. Each theory, a star in a constellation, we're still mapping. Let us drift deeper into the cosmic void, the stars now a quiet pulse in your mind. Dark matter's implications are profound, reshaping our understanding of the universe's structure and fate. Without it, galaxies wouldn't exist, stars would scatter, unable to form the dense clusters that birth solar systems. The universe's large-scale structure, a web of filaments and voids, owes its shape to dark matter's gravitational scaffolding, guiding matter into the patterns we see. It's a reminder that the cosmos is a collaborative effort with visible matter, stars, planets, us, playing a supporting role to an invisible lead. This hidden dominance raises existential questions. If 27% of the universe is dark matter and only 5% is normal matter, are we just a footnote in a larger story? It's as if the universe is a painting and we're only the highlights, not the canvas. Imagine yourself floating among the galaxies, their light a soft caress. Dark matter's mystery also fuels speculation about new physics. Its elusiveness suggests gaps in the standard model, the framework that describes particles and forces. Could dark matter be a portal to extra dimensions, as string theory proposes, or a remnant of a parallel universe? Some physicists, like Lisa Randall, explore ideas where dark matter interacts with itself, forming dark stars or disks, a shadow cosmos we cannot see. Others, like Catherine Fries, suggest it played a role in the Big Bang's aftermath, influencing the universe's expansion. These ideas are speculative, beautiful, like poems written in starlight. Yet they remind us that dark matter is a frontier, a clue to a deeper truth about reality. Let's explore dark matter's broader ripples, the cosmic web, now a faint shimmer in your mind. The search for dark matter is a global quest, uniting physicists in a shared pursuit. Experiments like the Large Hadron Collider hunt for dark matter particles by smashing protons, hoping to create WIMPs or axions. Space telescopes, like the upcoming Euclid mission, map its distribution through gravitational lensing, tracing its invisible hand. Yet the lack of direct detection keeps the mystery alive, a challenge that's both frustrating and exhilarating. It's like searching for a lost key in a dark room, knowing it's there, because the door stays locked. This quest also touches philosophy, echoing ancient questions about the unseen, Plato's shadows on the cave wall, invisible forces in mythology. Are these early echoes of dark matter, humanity's intuition that reality hides more than it shows? Picture the galaxy again, its spiral arms, a glowing testament to dark matter's pull. The concept resonates with human experience, reflecting our own encounters with the unseen. We trust forces we can't touch, love, faith, gravity, because we see their effects. Dark matter is a cosmic mirror, reminding us that much of life is felt, not seen, that meaning often lies in the invisible. It's a comforting thought, isn't it? The idea that the universe, like our lives, is shaped by forces beyond our sight, yet real in their impact. As you lie there, your body sinking into the mattress, let dark matter be a lullaby, its rhythm soothing your thoughts into a gentle haze. There's no need to see the invisible tonight. It's enough to ponder it, to let its quiet mystery wrap around you like a dream, guiding you toward peace. The debate around dark matter is a galaxy of its own, filled with voices chasing its truth. Some, like physicist Dan Hooper, bet on WIMPs, citing their fit with cosmology's models. Others, like Stacy McGaugh, explore modified gravity, questioning dark matter's necessity. There's no consensus, only a deepening mystery that invites wonder. Dark matter's power lies in its elusiveness, its ability to provoke without resolving, a perfect puzzle for quiet reflection as you drift towards sleep. This tale of an invisible force is just one light in the constellation of physics concepts we're exploring tonight. Each will illuminate another facet of the universe, revealing the strange, beautiful truths that shape our reality. From dark matter's silent pull, we'll drift to a force that drives the cosmos apart, accelerating its expansion into the unknown. Picture the universe stretching, pushed by an unseen energy that defies our grasp. What is this dark energy that shapes our fate? Close your eyes. Let the galaxy's glow fade into the quiet pulse of an expanding void. And let's drift into the next mystery, where the universe begins to race outward. The cosmos stretches before you, a vast expanse of stars and galaxies, their light a delicate shimmer against the infinite dark. Yet as you gaze, you sense a restless energy, an unseen force pushing these distant lights farther apart, stretching the universe like a balloon that never stops growing. This is dark energy, a mysterious entity driving the universe's accelerating expansion, a phenomenon so enigmatic it defies our understanding of physics itself. Discovered only in the late 20th century, dark energy is estimated to make up 68% of the universe. Sees mass energy, dwarfing the matter we see and touch. It's not just a force, it's a riddle that shapes the cosmos's fate, asking, what fuels this relentless growth, and where will it lead? As you settle into the soothing rhythm of this video, let's drift through this expanding void, letting dark energy's quiet mystery unfold like a whisper across the stars, guiding your mind toward a restful, contemplative sleep. This isn't a mere footnote in cosmology. It's a seismic shift, a discovery that turned our view of the universe upside down and opened questions that echo through science and philosophy. Imagine the universe as a vast ocean, It's galaxies like ships drifting on its surface. For billions of years, we thought gravity would slow their drift, perhaps pulling them back in a cosmic collapse. But in 1998, astronomers found the opposite. The universe isn't slowing, it's speeding up, its expansion accelerating, as if propelled by an invisible wind. This wind is dark energy, a force that counteracts gravity, pushing space itself to stretch ever faster. It's a concept that challenges our understanding of energy, matter, and the cosmos's destiny, suggesting that much of reality is driven by something we can't see or touch. As you lie there, your breath slow and even, let's sail through this cosmic ocean, exploring a paradox that races the universe toward an unknown horizon. Let's drift into the void, the stars receding like lanterns on a tide. Dark energy's discovery was a shock, born from observations of distant supernova, exploding stars that act as cosmic yardsticks. In the 1990s, two teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, studied Type 1a supernova, which have consistent brightness, allowing astronomers to measure their distance. They expected to find the universe's expansion slowing, a sign of gravity's pull. Instead, they found these supernovae were farther away than predicted, their light dimmer, suggesting the universe was expanding faster now than in the past. This 1998 revelation, which earned the trio a Nobel Prize in 2011, pointed to a repulsive force, dark energy driving galaxies apart. It's like discovering your ship is caught in a current racing toward an unseen shore with no map to guide you. Picture yourself floating among the galaxies, their light a faint glow against the dark. Dark energy is often linked to the cosmological constant, a concept Albert Einstein introduced in 1917 to balance his equations of general relativity, aiming for a static universe. When Edwin Hubble showed the universe was expanding, Einstein called the constant his greatest blunder. Yet dark energy revived it, suggesting a uniform energy field permeating space, exerting negative pressure that accelerates expansion. Unlike matter, which clumps into stars and planets, dark energy is smooth, distributed evenly, driving the universe's growth. Without gathering, it's as if space itself is infused with an invisible fuel, pushing its boundaries outward, stretching the cosmic canvas with every passing moment. Take a moment. Let the galaxy's glow soften into a quiet hum. The nature of dark energy is one of cosmology's deepest mysteries, a puzzle with no clear solution. The cosmological constant is one model, but others propose dynamic fields like quintessence, a form of energy that varies over time and space. Some theories even suggest dark energy is an illusion, a flaw in our understanding of gravity, with models like modified gravity challenging Einstein's framework. Each idea is a thread in a cosmic tapestry woven from observations of supernovae, galaxy clusters, and the cosmic microwave background, the Big Bang's afterglow. These measurements, from telescopes like Hubble and Planck, confirm dark energy's dominance, yet its essence remains elusive. It's like chasing a shadow that moves with you, always just out of reach. A mystery that humbles even the sharpest minds. Let's drift deeper into the expanding void, the stars now a distant shimmer in your mind. Dark energy's implications are profound, reshaping our view of the universe's past, present, and future. In the early universe, matter and gravity dominated, slowing expansion as galaxies formed. But about 5 billion years ago, dark energy took over, its repulsive force overpowering gravity, accelerating the cosmos's growth. This shift marks a turning point, a moment when the universe began racing toward a fate we're still unraveling. If dark energy is a constant, as the cosmological constant suggests, the universe will expand forever, cooling into a dark, empty void where stars burn out and galaxies drift beyond reach. It's a lonely vision, a big freeze where entropy reigns, yet it's strangely serene, like a symphony, fading into silence. Imagine yourself gazing across the cosmic ocean, the galaxies receding like ships into the night. Alternative fates exist, each tied to dark energy's nature. If it's dynamic, like quintessence, it could weaken, allowing gravity to pull the universe into a big crunch, a collapse that might spark another Big Bang. Or it could strengthen, tearing galaxies, stars, even atoms apart in a big rip, a violent end to reality itself. These scenarios are speculative, but they highlight dark energy's power to shape the cosmos's destiny. It raises existential questions. If the universe is doomed to fade, what's the meaning of our fleeting moment within it? If it cycles or tears, what's our place in its rhythm? It's as if the universe is a story, and dark energy is its final chapter, one we're still writing, each possibility a thread in a cosmic narrative. Let's explore dark energy's broader ripples, the cosmic void, now a quiet pulse in your mind. The discovery of dark energy has revolutionized cosmology, forcing us to rethink the universe's composition. Normal matter, stars, planets, us, makes up just 5% of the universe. Cosmos, dark matter, the invisible glue of galaxies, accounts for 27%. Dark energy, this mysterious force, dominates at 68%, a humbling reminder that most of reality is beyond our grasp. This cosmic pie chart challenges the standard model of particle physics, which has no clear candidate for dark energy. Some propose it's vacuum energy, the quantum buzz of empty space, but calculations predict a value far too large, a mismatch called the cosmological constant problem. Others explore string theory's extra dimensions or modified gravity, each a leap into the unknown, like explorers charting a sea with no horizon. Picture the universe expanding, its edges racing outward, a silent tide. Dark energy's discovery is a saga of human curiosity, sparked by the supernova observations of the 1990s. The team's findings overturned decades of assumptions, showing that the universe's fate wasn't a slow deceleration, but a relentless sprint. Further evidence from galaxy surveys like the Sloan Digital Sky Survey and cosmic background measurements solidified dark energy's role, painting a picture of a cosmos driven by an unseen force. Yet its nature remains a mystery, fueling experiments like the Dark Energy Survey and the upcoming Euclid mission, which map the universe's expansion with unprecedented precision. It's like piecing together a puzzle with half the pieces missing. Each new clue deepening the enigma, each discovery a star in a constellation we're still tracing. Let's linger in the void, the galaxies now a faint glow in your mind. Dark energy also resonates with human experience, echoing our own questions about purpose and permanence. We build lives, relationships, dreams, knowing they'll fade, yet we persist, finding meaning in the fleeting. Dark energy's relentless push mirrors this, a force that drives the universe toward an uncertain end, yet leaves room for beauty in itself. It's unfolding. It's a comforting thought, isn't it? The idea that even in a cosmos racing apart, there's space for wonder, for stories told under the stars. As you lie there, your body sinking into the mattress, let dark energy be a lullaby, its rhythm soothing your thoughts into a gentle haze. There's no need to grasp the cosmos's fate tonight. It's enough to ponder it, to let its quiet mystery wrap around you like a dream, guiding you toward peace. The debate around dark energy is a cosmos of its own, filled with voices seeking its truth. Some, like physicist Sean Carroll, back the cosmological constant, citing its simplicity. Others, like Paul Steinhardt, explore dynamic models like quintessence, hoping to explain its evolution. Critics like Subir Sarkar question the supernova data, suggesting alternative explanations for acceleration. There's no consensus, only a deepening mystery that invites wonder. Dark energy's power lies in its ambiguity, its ability to provoke without resolving, a perfect puzzle for quiet reflection as you drift toward sleep. This tale of an accelerating cosmos is just one light in the constellation of physics concepts we're exploring tonight. Each will illuminate another facet of the universe, revealing the strange, beautiful truths that shape our reality. From dark energy's relentless push, we'll drift to a cosmic limit that binds our dreams of exploration, a barrier nothing can cross. Picture a spaceship racing toward the stars, halted by the unyielding speed of light. What does it mean to be bound by this cosmic rule? Close your eyes. Let the void's pulse fade into the quiet hum of a starship's engine. And let's drift into the next mystery, where light itself becomes a wall. The stars blaze above a cosmic sea of light stretching into the infinite, each one a beacon calling you to explore. You're aboard a sleek spaceship, its engines roaring as you push through the void. Faster, ever faster, chasing the dream of distant worlds. The galaxies blur, the universe a kaleidoscope of motion. But no matter how hard you push, you can't break through an invisible wall. A cosmic speed limit that holds you back. This is the speed of light barrier, a universal constant set at 299,792,458 meters per second. An unbreakable rule in Einstein's theory of relativity that defines the structure of space and time. It's not just a limit, it's a paradox that shapes our understanding of the universe, asking, why can't we go faster? And what does this barrier mean for our dreams of the stars? As you settle into the soothing rhythm of this video, let us race through the cosmos, letting the speed of light's quiet mystery unfold like a starlit veil, guiding your mind toward a restful, contemplative sleep. This isn't a mere technical constraint. It's a cornerstone of modern physics, a truth that binds the universe's laws and challenges our ambitions to explore its farthest reaches. Imagine light itself, a photon streaking through the void, untethered by mass, moving at the ultimate speed. Nothing with mass, your spaceship, a particle, even a dream, can match it. No matter how much energy you pour in. The speed of light, denoted c in Einstein's equations, is more than a number. It's a boundary, a cosmic line that separates possibility from impossibility. It's a concept that's both humbling and awe-inspiring, grounding our technology while fueling our imagination. A paradox that reminds us the universe has rules we can't break, yet invites us to wonder, what lies beyond. As you lie there, your breath slow and even, let's push against this barrier, exploring a limit that shapes the cosmos and our place within it. Let's launch into the stars. The spaceships hum, a steady pulse beneath your feet. The speed of light barrier is rooted in Einstein's special theory of relativity, published in 1905, a revolutionary framework that unified space and time. Einstein showed that as an object with mass accelerates, its energy increases, but so does its effective mass, a relativistic effect that grows dramatic near light speed. To reach 299,792,458 meters per second, you'd need infinite energy, an impossibility that makes the barrier absolute. It's like running toward a horizon that recedes faster the closer you get, always out of reach. This limit applies to anything with mass, spaceships, particles, even information, ensuring that cause precedes effect, a principle called causality that keeps the universe's timeline intact. Light, massless and free, dances at this speed, a cosmic constant that's the same for all observers, whether you're on Earth or racing through space. Picture yourself at the helm, the stars streaking past like fireflies in a cosmic wind. The speed of light's universality is one of relativity's strangest truths. If you're moving at half-light speed and shine a flashlight, the light doesn't travel at c plus your speed. It still moves at c, no faster, no slower. This invariance, confirmed by experiments like the Michelson-Morley experiment in 1887, shattered classical physics, showing that space and time adjust to keep c constant. Clocks slow, lengths contract, and the universe bends to preserve this limit, a phenomenon called Lorentz transformation. It's as if the cosmos is a symphony, and the speed of light is its tempo, unchanging no matter how the players move. This constancy is why time dilation occurs. Travel near c, and your clock ticks slower compared to Earth's. A real effect seen in particles like muons, which live longer when sped up in accelerators. Take a moment. Let the starships hum soften into a gentle glow. The implications of the speed of light barrier are profound, shaping not just physics, but our dreams of exploration. It limits space travel, making distant stars unreachable within a human lifetime. It's a barrier that confines us to our cosmic neighborhood, a humbling reminder of our scale against the universe's vastness. Yet it also protects the universe's order. If you could exceed c, you could send signals backward in time, disrupting causality. Effects could precede causes, creating paradoxes like stopping an event before it happens. It's as if the universe has a built-in safeguard, ensuring its story unfolds in sequence. Let's drift deeper into the cosmos. The stars now a quiet pulse in your mind. The speed of light's history is a saga of human curiosity. From Galileo's early attempts to measure light's speed, to Ole Romer's 1676 observation of Jupiter's moons, which hinted at a finite value. By the 19th century, precise measurements like those by Hippolyte Fizeau pinned it down, paving the way for Einstein's insights. His 1905 paper on special relativity, written at age 26, was a leap that unified space, time, and light, predicting phenomena like time dilation and length contraction, later confirmed by experiments with atomic clocks and particle accelerators. The speed of light is woven into every corner of physics, from E equals mc squared, which ties energy to mass, to the equations of electromagnetism, where C links electric and magnetic fields. It's a constant that's both practical and profound, a thread that stitches the universe together. Imagine yourself gazing out, the starship's window, the universe, a canvas of light and shadow. The barrier's implications stretch into technology, grounding our world in relativity's truths. GPS satellites, orbiting in weaker gravity, tick faster than Earth's clocks, requiring corrections based on C to stay accurate. Particle accelerators like CERN's Large Hadron Collider push protons to 99.999% of light speed. Their increased mass, a testament to the barrier's reality. Yet the limit fuels S. Science fiction dreams of warp drives or wormholes, inspired by physicists like Miguel Alcubierre, who proposed theoretical warp bubbles that contract space ahead and expand it behind, sidestepping C. These ideas, rooted in general relativity, require exotic matter and vast energy, remaining speculative, like stars we can see but never touch. Let's explore the barrier's broader ripples, the starship now a faint hum in your mind. The speed of light shapes our understanding of the universe's history and fate. Light from distant galaxies traveling at sea reaches us after billions of years, letting us peer into the past, a cosmic time machine. The finite speed of light creates a light cone, defining what we can influence or observe, a boundary that isolates us in a universe where signals take eons to cross. This isolation raises philosophical questions. If we rebound by C, are we alone in our cosmic moment, unable to connect with distant civilizations? It's a poignant thought, echoing our human longing to reach beyond, to touch the stars. Yet it's also serene, a reminder that our place in the cosmos is both small and precious. Picture yourself at the helm. Again, the stars a glowing testament to light's rule. The barrier also resonates with human experience, mirroring our own limits and ambitions. We strive, we dream, yet face boundaries, time, distance, mortality that we can't cross. The speed of light is a cosmic mirror reflecting this truth. Some limits are absolute, yet they spur creativity, pushing us to find new paths, like explorers charting rivers they can't ford. It's a comforting thought, isn't it? The idea that even in a universe with unbreakable rules, there's room for wonder, for stories told under the stars. As you lie there, your body sinking into the mattress, let the speed of light be a lullaby, its rhythm soothing your thoughts into a gentle haze. There's no need to break the barrier tonight. It's enough to ponder it, to let its quiet mystery wrap around you like a dream, guiding you toward peace. The debate around the speed of light is a cosmos of its own, filled with voices chasing its truth. Some, like physicist Kip Thorne, explore theoretical shortcuts like wormholes, bridges in spacetime that might bypass causality. Others, like Sabine Hossenfelder, argue such ideas are speculative, rooted in untested physics. Experiments, from particle accelerators to gravitational wave detectors, confirm light's constancy, yet the quest to understand its full nature continues. For a quantum theory of gravity unifying relativity with quantum mechanics hints at deeper truths where C might play a new role. There's no final answer, only a deepening mystery that invites wonder. The barrier's power lies in its absoluteness, its ability to provoke without yielding, a perfect puzzle for quiet reflection as you drift toward sleep. This tale of an unbreakable limit is just one light in the constellation of physics concepts we're exploring tonight. Each will illuminate another facet of the universe, revealing the strange, beautiful truths that shape our reality. From the speed of light's cosmic boundary, we'll drift to a theory where the universe loops in endless cycles, a rhythm of creation and collapse. Picture the cosmos pulsing, reborn through infinite Big Bangs. What does it mean to live in a cyclic universe? Close your eyes, let the starships hum fade into the quiet beat of a cosmic heart. Let's drift into the next mystery, where the universe begins to breathe. The cosmos breathes a vast expanse of stars and shadows, pulsing with a rhythm older than time itself. Picture the universe as a grand symphony, its galaxies swelling and fading, each note a cycle of creation and collapse, an endless loop of big bangs and big crunches. This is the cyclic universe model, a theory that imagines reality not as a singular event, but as a cosmic heartbeat oscillating through infinite births and deaths. Proposed by physicists like Paul Steinhardt and Neil Turok, it suggests our universe is just one pulse in an eternal sequence, each cycle sparking a new cosmos with its own stars, planets, and stories. It's a concept that challenges our sense of beginnings and endings, asking, if the universe loops forever, what's our place in its eternal rhythm? As you settle into the soothing rhythm of this video, let's drift through this cycling cosmos, letting the theory's gentle mystery unfold like a starlit breath, guiding your mind toward a restful, contemplative sleep. This isn't just a speculative idea. It's a profound vision that redefines the universe's narrative, offering an alternative to the linear story of a single Big Bang fading into a cold, empty void. Imagine the universe not as a one-act play, but as a cycle of performances, each act a new reality born from the ashes of the last. Unlike the standard model, where the Big Bang is a singular origin followed by eternal expansion, the cyclic universe proposes a series of expansions and contractions, each cycle beginning with a hot, dense spark and ending in a collapse that seeds the act. Next, it's a theory that blends cosmology with philosophy, touching on questions of eternity, renewal, and our fleeting moment in the cosmic dance. As you lie there, your breath slow and even, let's ride the pulse of this cosmic heartbeat, exploring a paradox that weaves infinity into the fabric of existence. Let's drift into the cosmic void, the air shimmering with the echo of countless cycles. The cyclic universe model, developed in the early 2000s by Steinhardt and Turok, builds on earlier ideas about an oscillating cosmos. In the standard Big Bang model, the universe began 13.8 billion years ago as an infinitely dense point, expanding and cooling to form galaxies driven by dark energy's relentless push. But the cyclic model imagines a different fate. After billions of years of expansion, dark energy weakens, gravity takes over, and the universe contracts in a big crunch, collapsing into a dense, hot state that sparks a new Big Bang. This process repeats infinitely, each cycle lasting trillions of years, a cosmic rhythm that avoids a singular origin. It's like a phoenix burning to ash, only to rise anew. each universe a fresh canvas for stars and life. Picture yourself floating in the aftermath of a big crunch, the universe a searing point of light, ready to bloom again. The cyclic model draws on string theory, a framework where particles are tiny vibrating strings and extra dimensions exist curled up beyond our sight. Steinhardt and Turok propose that our universe is a three-dimensional brain floating in a higher dimensional space, colliding with another brain to trigger each Big Bang. These collisions, occurring every trillion years, release energy that mimics the Big Bang's conditions, creating a new cycle without a true beginning. It's as if the universe is a pair of cosmic symbols clashing to start each movement of the symphony, their rhythm eternal. Unlike the standard model, which struggles with the singularity, a point where physics breaks down, the cyclic model smooths it out, offering a continuous process that's both elegant and speculative. Take a moment. Let the cosmic pulse soften into a gentle hum. The implications of the cyclic universe are profound, reshaping our view of time and existence. If reality loops infinitely, there's no ultimate beginning or end, no single moment that defines the cosmos. Time becomes a circle, not a line, challenging our linear sense of history. In each cycle, new stars form, new planets spin, new lives unfold. Perhaps even new versions of you, living stories, similar yet distinct. It's a vision that's both comforting and disorienting, suggesting that our universe is one of countless iterations, each a fresh chance for creation. This eternity raises philosophical questions. If the universe repeats, is there purpose in its cycles? Or is there anything? It a cosmic treadmill running without destination. It's like wondering if a song played forever loses meaning or gains it through its endless refrain. Let's drift deeper into the cycling cosmos, the stars now a faint shimmer in your mind. The cyclic model's appeal lies in its solutions to cosmological puzzles. The standard Big Bang model struggles with the flatness problem. Why is the universe's geometry so balanced? And the horizon problem, why are distant regions so uniform? Inflation, a rapid expansion in the universe's infancy, addresses these, but the cyclic model offers an alternative. Each cycle resets the universe's conditions, smoothing out wrinkles and ensuring flatness, like ironing a cosmic sheet. The model also avoids the need for a singular origin, sidestepping the question of what came before the Big Bang by proposing an eternal process. It's a theory that's mathematically complex, rooted in string theory's extra dimensions, yet it's elegant, a vision of a universe that breathes without beginning or end. Imagine yourself caught in the pulse of a new cycle, the universe blooming around you in a blaze of light. The cyclic model's history is a tale of bold ideas, building on earlier oscillating models from the 20th century. In the 1930s, physicist Richard Tolman explored cyclic cosmologies, but they faltered against entropy's rise, which suggested each cycle would grow disordered. Steinhardt and Turok's model, introduced in 2002, revived the idea with string theory's brains, proposing that entropy resets in each cycle, keeping the universe vibrant. Their work, detailed in papers like A Cyclic Model of the Universe, drew on advances in string theory by physicists like Lisa Randall, offering a framework where brain collisions drive cosmic rebirth. It's a fascinating concept. Theory that's gained attention, though it remains speculative, a star in the constellation of cosmology, still awaiting confirmation. Let's explore the model's broader ripples. The cosmic void, now a quiet beat in your mind. The cyclic universe has implications for our understanding of time, causality, and purpose. If reality cycles, time is infinite, yet each cycle is finite. A paradox that blends eternity with ephemerality. It suggests that our universe, with its 13.8 billion years, is just a chapter, not the whole book, raising questions about our role in this rhythm. Are we unique or one of countless echoes? The model also touches on the anthropic principle, the idea that our universe's laws are tuned for life because we're here to observe them. In a cyclic cosmos, each cycle might vary slightly, producing worlds where life thrives or fails. A cosmic lottery where we're one winner among many. It's like imagining every performance of a play has a new cast, each telling a story both familiar and fresh. Picture the universe collapsing, its light converging into a single searing point. The cyclic model's implications stretch into technology and observation, though testing it is daunting. Unlike the standard model, which weaves traces like the cosmic microwave background, the cyclic model predicts subtle signals, gravitational waves, or brain collision patterns that future telescopes like the Simons Observatory might detect. These tests are speculative, but they fuel research pushing cosmology's boundaries. The model also inspires philosophy, echoing ancient ideas of cyclical time in Hinduism or Stoicism, where existence loops through creation and destruction. It's a reminder that our questions about eternity are timeless, woven into both science and myth, like stars that shine across millennia. Let's linger in the cosmic pulse, the universe now a soft glow in your mind. The cyclic universe resonates with human experience, reflecting our own cycles of growth and renewal. We live through seasons, through births and endings, finding meaning in repetition, daily routines, annual traditions, the rhythm of breath. The model is a cosmic mirror, suggesting that the universe too finds purpose in its cycles, each one a chance to begin anew. It's a comforting thought, isn't it? The idea that even in a cosmos of infinite loops, there's space for stories, for lives like yours, played out under the stars. As you lie there, your body sinking into the mattress, let the cyclic model be a lullaby, its rhythms soothing your thoughts into a gentle haze. There's no need to grasp eternity tonight. It's enough to ponder it, to let its quiet mystery wrap around you like a dream, guiding you toward peace. The debate around the cyclic universe is a cosmos of its own, filled with voices seeking its truth. Supporters like Steinhardt argue it solves cosmological puzzles without inflation's complexities. Critics, like Sean Carroll, question its reliance on untested string theory, favoring the standard model's empirical grounding. There's no consensus, only a deepening mystery that invites wonder. The model's power lies in its vision, its ability to provoke without resolving, a perfect puzzle for quiet reflection as you drift toward sleep. This tale of a pulsing cosmos is just one light in the constellation of physics concepts we're exploring tonight. Each will illuminate another facet of the universe, revealing the strange, beautiful truths that shape our reality. From the cyclic universe's eternal rhythm, we'll drift to a paradox where reality itself might be a construct, a simulation running on a cosmic computer. Picture your life, every star and thought, as code in a vast machine. Are we real or digital dreams? Close your eyes. Let the cosmic pulse fade into the quiet hum of a digital cosmos, and let's drift into the next mystery where existence begins to blur. The night is deep, a velvet expanse where stars pulse like heartbeats, each one a story woven into the fabric of the cosmos. You lie beneath this celestial canopy, your breath a soft rhythm against the silence, when a question slips into your mind. Quiet at first, then all-consuming. What if this moment, your breath, the stars, the very texture of your existence, isn't real? What if it's all code, a simulation so flawless you'd never suspect, running on a computer vast enough to cradle the universe? This is the simulation argument, a thought experiment proposed by philosopher Nick Bostrom in 2003, a riddle that doesn't just challenge physics, but probes the essence of reality itself. It suggests we might be characters in a cosmic program, unaware of the code behind our lives, asking, if our world is a simulation, what does it mean to be real? As you settle into the soothing rhythm of this video, our final stop in this cosmic journey, let's drift through this digital cosmos, letting the argument's gentle mystery unfold like a starlit dream, guiding your mind toward a restful, contemplative sleep. This isn't a sci-fi fantasy spun for thrills. It's a profound hypothesis that blends physics, philosophy, and technology, forcing us to question the ground beneath our feet. Imagine waking to your morning routine, the warmth of coffee in your hands, the hum of the world outside, the weight of your thoughts. It feels solid, undeniable, real. But what if every sensation, every memory, every flicker of starlight is a line of code, a digital illusion crafted with such precision it mimics reality perfectly? Bostrom's argument doesn't claim we're definitely simulated. It posits that given certain conditions, it's statistically more likely than not. It's a question that's both exhilarating and unsettling, like floating in a sea of stars, wondering if the waves are water or data. It asks us to reconsider existence, to hold the possibility that our reality might be a creation, yet it does so with a calm invitation. What if the truth is stranger than we ever dreamed? As you lie there, your breath slow and even, let's dive into this cosmic code, exploring a paradox that blurs the line between real and virtual. Let's begin under the stars, the universe a shimmering expanse above you. Bostrom's simulation argument rests on three possibilities, only one of which can be true. First, advanced civilizations, human, alien, or otherwise, never reach the technological ability to create simulations so realistic they mimic consciousness. Perhaps they go extinct, their progress stalls, or they lack the resources to build such machines. Second, advanced civilizations develop this technology but choose not to run simulations, perhaps for ethical reasons, like sparing simulated beings the burden of existence, or because they are uninterested, like artists who never pick up the brush. Third, advanced civilizations create countless simulations, each a universe with sentient beings who believe they're real, like us. If this third scenario holds, the number of simulated realities would dwarf the single base reality, the original non-simulated world. making it statistically likely that we are in a simulation, not the one true cosmos. It's like drawing a single red marble from a jar filled with billions of blue ones. The odds favor the blue, the simulated. Picture yourself floating in this digital cosmos, the stars now glints of code in a vast program. The third possibility is the argument's heart, the one that makes your mind real. If a civilization achieves the computing power to simulate entire universes, complete with conscious beings, they'd likely create many experiments to study history, virtual worlds for entertainment, or simulations to test cosmic theories. Each simulation could hold billions of sentient minds, each as real to themselves as you are to yourself. The math is relentless. With trillions of simulated worlds, the chance you're in the one base reality becomes vanishingly small, like picking a single star from a galaxy. Bostrom's argument is neutral. It doesn't prove we're base reality. Simulated only, that the odds tilt heavily toward it if simulations are possible. It's a statistical trap, the cosmic lottery, where the prize is reality itself, and the stakes are your sense of existence. Take a moment. Let the starlight's glow soften into a quiet hum. The simulation argument's implications are profound, touching every corner of physics, philosophy, and human experience. If we are in a simulation, what does that mean for your life, your choices, your loves? Does it diminish the warmth of a friend's smile, the ache of a loss, or the thrill of a starry night? The paradox lies in the tension. Your experiences feel vivid, undeniable, yet they could be digital, a script running on a machine. It's like reading a novel, so immersive you forget it's fiction, only to wonder if you're a character in someone else's code. The argument challenges our assumption of a solid, singular reality, suggesting we might be a creation. Yet it leaves room for meaning, for the possibility that our digital lives are as valid as any real ones. Let's drift deeper into this coded cosmos, the stars now a faint pulse in your mind. The argument draws on ideas rooted in both ancient philosophy and modern technology. Plato's allegory of the cave, where prisoners see only shadows of a truer reality, echoes the simulation's premise. Descartes' evil demon deceiving our senses is a precursor to the idea of a programmed world. Today's technology brings these musings into focus. Video games like The Sims create virtual lives, while virtual reality headsets immerse us in artificial worlds. If our descendants, or an alien civilization, achieve the computing power to simulate conscious minds, why wouldn't they? They might run simulations to explore history, test physical laws, or simply for amusement like we binge-watch shows. Some estimate we are decades from simulating basic consciousness, a stepping stone to universes in silicon. Imagine yourself as a flicker in this digital sea, the cosmos, a program humming around you. The argument's implications stretch into physics, where the universe's structure might hint at its artificiality. Some physicists, like Silas Bean, propose looking for glitches, patterns in cosmic rays, or limits in physical laws, like pixels in a video game. Quantum mechanics, with its probabilistic nature, could reflect a digital framework where reality renders only when observed, like a game, saving processing power. The universe's fine-tuned constants, gravity's strength, the electron's charge, might suggest a coded design optimized for life. Yet skeptics argue these are anthropic biases that we see tuning because we exist to observe it. The debate is a cosmic tug-of-war, each side pulling at the threads of reality, seeking signs of code or chaos. Let's explore the argument's broader ripples. The digital cosmos, now a quiet glow in your mind. If we re-simulated, who's running the show? Future humans, aliens, or an AI god? Are they watching, tweaking variables, or have they moved on? Our simulation a forgotten program. What happens if it ends? Does our world blink out like a powered-down screen, or do we persist unaware of the shutdown? These questions touch philosophy, echoing existentialism's search for meaning in an uncertain world. If our reality is code, does it lessen the value of a sunset, a laugh, a life? Bostrom argues it might not. Your experiences are real to you, whether coded or not, like a dream that feels vivid until you wake. It's a comforting thought, suggesting that meaning lies in the moment, not the medium. Picture yourself under the stars again. Their light, a coded symphony. The argument resonates with modern life, where technology blurs real and virtual. Social media curates lives that feel perfect. Video games immerse us in other worlds, and AI mimics human thought. These are echoes of the simulation, hints of a future where reality and illusion merge. The argument also raises ethical questions. If we create simulations with conscious beings, are we gods or monsters? Should we run them, knowing they'll suffer, love, die? It's a mirror to our own existence. If we're simulated, do we have rights, or are we just data? These questions, heavy yet serene, invite reflection without demanding answers. A gentle pull toward wonder as you drift toward sleep. Let's linger in the digital cosmos, the stars now a soft hum in your mind. The simulation argument's history is brief but potent. Born in Bostrom's 2003 paper, Are You Living in a Computer Simulation? It built on earlier ideas, like John Conway's Game of Life, a cellular automaton mimicking complex systems, and sci-fi like The Matrix. Bostrom's work sparked debates across disciplines, from Elon Musk's public musings to physicist David Deutsch's quantum arguments. Experiments to test the hypothesis, like searching for computational limits in physics, are speculative, but they fuel research, pushing the boundaries of cosmology and computing. The argument's power lies in its ambiguity, its ability to provoke without proving, a perfect riddle for a curious mind. Let's explore the argument's human resonance, the cosmos now a quiet pulse in your heart. We all seek reality, yearning for truths that anchor us, love, purpose, connection. The simulation argument is a cosmic mirror reflecting this quest, suggesting that reality might be layered, yet our experiences remain vivid, true in their feeling. It's a comforting thought, isn't it? The idea that even if we're code, our stories matter, our moments shine. As you lie there, your body sinking into the mattress, let the argument be a lullaby, its rhythm soothing your thoughts into a gentle haze. There's no need to know the truth tonight. It's enough to ponder it, to let its quiet mystery wrap around you like a dream, guiding you toward peace. The debate around the simulation argument is a galaxy of voices, from physicists like Max Tegmark, who explore computational signatures, to skeptics like Sabine Hossenfelder, who question its testability. There's no consensus, only a deepening mystery that invites wonder. The argument's power lies in its open-endedness, a perfect puzzle for quiet reflection as you drift toward sleep. This tale of a coded cosmos is the final light in the constellation of physics concepts we've explored tonight. Each has illuminated a facet of the universe, revealing the strange, beautiful truths that shape our reality. As we leave the stars behind, let their glow carry you into dreams where questions dissolve and mysteries bloom. Sleep well, and may your mind drift through the cosmic wonders we've unveiled, each one a star to guide you through the night.